Hello and welcome to Lecture 9. This is hopefully our very last remote lecture. Beginning Monday, we're scheduled to be back in person. I did change our classroom. We're now going to have our class in the Arts Building, room 1043. That's down in that area next to the Tims. So we're moving over there because that room is lecture capture enabled. All of the lectures, I am going to record them with lecture capture. If for whatever reason you're not able to make it to a live class, you can at least catch the recording of it. So just get in touch with me if you have any questions. In today's lecture, we're going to do one last example about calculating a capacitance, and then we're going to get on to talking about capacitors in series and in parallel, so capacitors in circuits.
Let's look at a capacitor example now that looks a little funny, but it's still the same thing as what we've been doing. Two concentric spherical conducting shells are separated by a vacuum. The inner shell has a charge plus Q and the outer shell has a charge of minus Q. So what's going on here? You might imagine two balloons, one smaller inside the other. So this is one shell, the peach one. This is another shell, the blue one. If you're thinking physically, how does this work? They're probably held in place by some kind of glass rod or something. So there's something there to keep them from touching each other and from falling down. Okay, so that's the setup. We've got two plates equal and opposite charge. So that means this is going to act as a capacitor and we want to find the capacitance. To make this a little bit easier to see, I took a two-dimensional slice of our spherical capacitor here. The inner shell is the peach one, so that looks like a circle when we draw it in 2D. That has a radius that we call RA, and it carries a charge of plus Q. Our outer shell, that's the light blue one. I've drawn that over here. That has a radius of RB, and it carries a charge of negative Q. So we have two conducting surfaces, equal and opposite charge, separated by a distance. We'll use our familiar expression of C equals Q over delta V to find the capacitance. So what we're going to have to do is find the potential difference between these two shells. So the potential difference between the shells means we need to find the potential at point A, so the potential at a distance of RA, subtract the potential at a distance of RB. That's going to be our delta V. And that's what we're going to use in our expression for capacitance. So if we want to find the potential, it would help to know the electric field. How do we find the electric field? We use Gauss's law. So we start by drawing a Gaussian surface. Our Gaussian surface is going to be a sphere with radius r. We'll write down Gauss's law, which says the net electric flux is the integral of E dot dA equals the net charge enclosed by the Gaussian surface divided by epsilon naught. So we follow this process, we show all the steps. That's been done in a previous lecture if you need to review how to do that. And we see that E is equal to K times Q divided by R squared, where K is Coulomb's constant 1 over 4 pi epsilon naught. Q inside our Gaussian surface is just the charge on the inner shell, it's plus Q. All right, after we have an expression for our electric field, we can use the relationship between field and potential to find an expression for the potential. So we know that change in potential is minus the integral of E dot ds. And if we put in our expression for our electric field and we do our integral, so again, we'll do this and we'll say show steps like we've done in a previous lecture. We find that the electric potential at any one point is equal to K times Q divided by R, where Q is that same charge inside the Gaussian surface. Okay, this gives us an expression to find our electric potential. This means that the potential at surface RA is equal to K times the charge divided by RA, and our potential at surface B, just as we reach surface B, is K times Q divided by RB. Our change in potential then, delta V, is V of RA subtract V of RB equals KQ over RA subtract KQ over RB. Take my KQ outside. 1 over RA, subtract 1 over RB. Can leave it like this, or we can find a common denominator to write KQ outside of RB, subtract RA, divided by RA times RB. Okay, Here's an expression for our potential. We can use this now in our equation for capacitance and find the capacitance of this structure. Let's find our capacitance now. It's the charge divided by delta V. So that's our charge divided by K. Remember, K is 1 over 4 pi epsilon naught times Q times RB subtract RA divided by RA times RB. Okay, there's everything filled in. Notice we've got a Q in our numerator and our denominator, so those cancel. Our 4 pi over epsilon naught is the denominator of the denominator, so that belongs up in the numerator. So C is equal to 4 pi epsilon naught. Then that's times RA times RB divided by RB minus RA. So there's our expression for the capacitance of a spherical capacitor.